Hi, everybody. I guess I got started a little bit late here, but this is my first live stream on this channel, and today I'm going to talk about some basic properties of Fibonacci numbers. I assume most of you are familiar with them. If not, I'm going to start at the beginning. I'm going to start with the basics, and I'll discuss some of their useful properties. I'd like it if you guys left questions or comments. I have a chat window. You can use a chat window to ask me questions or leave comments if you want. Anyway, let's begin. And before I do, I think I should say a little word about this picture on this slide. This is what's called a Fibonacci spiral. And the numbers in these different squares. So there's a spiral. You notice that each portion of the spiral lies in a quadrant of a. It's a quadrant of a square, and these quadrants. These are circular quadrants, and they make up this Fibonacci spiral. And the numbers are just the size, the lengths of the sides of the spiral. There's a tiny spiral at the very beginning of like the one. I don't think you can see that, but I'll go into that later. Anyway, just one of the useful properties of Fibonacci numbers. But first, think I should say a little bit about Leonardo Fibonacci. He is actually known by a lot of different names, but we commonly know him as Fibonacci. He was a medieval Italian mathematician. He lived. We don't know the exact years he lived, but he lived from around 1170 to around 1250 AD, and he was from Pisa, Italy, I believe, and he was a friar. I guess most people at that time they worked for the church in one way or another, and he did too. But he was interested in math, and one of his big mathematical developments was his invention of the Fibonacci sequence, and it actually turns out he wasn't the first person to invent the Fibonacci sequence. He was the first European. I think Fibonacci numbers were already known in parts of Asia before then. I think as early as the 6th century AD, but that knowledge never came to the West. But Fibonacci did discover the Fibonacci sequence. As a matter of fact, he wrote this book. I mean, what's probably even bigger accomplishment for Fibonacci was that he wrote a book called Libera Bacci, where he basically introduced our modern system for doing math, including our decimal system and how we do like shifted and multiplication, how we use base 10, how we do carries and borrows and addition subtraction, how we do long division. All that was in his book, and we kind of owe all that to Fibonacci. And I think his book was something like 200 pages, but there was just 2 pages in his book devoted to Fibonacci numbers. And it was in connection with a problem he came up with involving rabbit breeding. And here's how he came up with a Fibonacci sequence. So you're supposed to imagine this is kind of an idealized scenario involving rabbits, but you're supposed to imagine you start with 2 rabbits, one single pair of rabbits, one male, one female, say at the beginning of the year, or late December if you like. And then the rules are that these are newborns. So you start with a newborn pair of rabbits, one male, one female. It takes a month for them to become fertile. So they have to grow up first. And then after 1 month, they become fertile. And once they become fertile, they start having kids. They start having other rabbits. Each month, each fertile pair of rabbits gives birth to a new pair of rabbits. And then the rabbits never die. That's another assumption. And then every month, every fertile pair of rabbits keeps producing another fertile pair of rabbits. And then you might wonder, well, how many rabbits do you have after a given number of months? Well, it turns out the number of rabbits is always a Fibonacci number. In January, you'll have one pair of rabbits. In February, you'll still have, or yeah, if you start in January with one pair, they're newborn at the beginning of the year. So, the beginning of the next month, February, you're still going to have one pair, but now they're 1 month old. In March, beginning of March, you're going to have your original pair of rabbits are now 2 months old, but those have given birth to another pair that's now 1 month old. And then the original pair is fertile, and now the new pair is also fertile, so that gives birth to another pair, and so on. And now you've added two pairs, you have three altogether, and you keep going like this, and you're going to always get a Fibonacci number. So 1, 1, 2, 3, 5, 8. After 6 months, you have 8 rabbits. After 12 months, it turns out you have 144 rabbits. So they grow pretty fast. And here's the rule. So you can kind of boil down this sequence to a very simple sequence defined by this recurrence relation. So we call it f sub n. And n is just the index. So f sub 0, n can be any positive integer greater than, or non-negative integer. So we define f0 to be 0, and we define f1 to be 1. And then for n greater than 1, we say fn is fn minus 1 plus fn minus 2. In other words, each new Fibonacci number in the sequence is the sum of the two previous ones. So we start with 0 and 1. And then that's so f0 is 0, f1 is 1, f2, that's the third number of the sequence. So that's 1 plus 0, that's 1. 2 is 1 plus 1. 3 is 2 plus 1. 5 is 3 plus 2, so on. I think you see how that works. Each number is just, this is a little more visual. So I think you can see here that every new number, the sequence is the sum of the previous two. That's how we define the Fibonacci sequence. And we have our initial conditions f0 is 0, f1 is 1, and fn equals fn minus 1 plus fn minus 2. That defines the Fibonacci sequence. These are just the first few elements. You can go higher, and here's a little bit of an extended list. And they grow pretty fast, like I said. F14, this is just the first 14 of them. F14 is already 377. Like I said, after 12 months, you'll have 144 rabbits. That was what Fibonacci put in his book. But if you want a couple more months, you'd have 377. So that's what the Fibonacci sequence is. And you can do a lot of really neat things with a Fibonacci sequence. I think I already showed you this slide. This is a little bit better picture. This is color-coded. But in the very center, I don't know if you can see that little tiny square at the very center of this picture. That's a square of size 1. So we start with a single square of size 1. That's f1. f1 is 1. And f2 is also 1. So right next to it, if you notice, there's another square just to the right of the tiny white square in the middle. There's a little pink square right next to it to the right. That's also size 1. f1 is 1. But then we start making them bigger. So then 1 plus 1 is 2. That's kind of convenient because we have two. Notice that we have two sides of length 1 on top of these two small squares. So now we can make a new square of side length 2. And then we can put another, these are all quarter circles we're drawing. This whole spiral, this is what's called the Fibonacci spiral. It's made up of all these different quarter circles in the radius of each quarter circle is a Fibonacci number. So the first two have a radius of 1. Third one has a radius of 2. Fourth one has a radius of 3. That's f4. Fifth one has a radius 5, 8, 13, 21. I think you see how it works. And it's a very good approximation to what's called a logarithmic spiral. It's not quite a logarithmic spiral, but it's very close. And you might think this is just kind of a theoretical, mathematical construction. It actually turns out that you get this in nature. Chamber nautilus is a good example. This is a cross section of a chamber nautilus shell. And this is a logarithmic spiral. I noticed that it looks pretty much like the Fibonacci spiral. Maybe not quite exactly, but very close. Same idea. So Fibonacci numbers and golden spiral, Fibonacci spirals seem to occur in nature, and not just in terms of nautilus shells or snail shells or whatever, but flowers. Flowers also exhibit Fibonacci numbers. It turns out that almost every flower, if you count the number of petals, it's almost always a Fibonacci number. So you'll notice, for instance, the one in the middle, the bottom middle, has 5 petals. And then some of these others, I think the one on the middle right has 8 petals. I'm not sure what these flowers are. I'm not an expert on but flowers. But if you count the number of petals in these flowers, I think you'll find that they're all equal to Fibonacci numbers. The one in the middle looks like it's got just 3 petals. So you have a lot of flowers with 3, 5, 8, 13. I think even 21 and 34 petals. Those are all Fibonacci numbers. But flowers with like 4 petals are extremely rare. And it's not just flowers. I mean, leaves on different plants too, like clovers. I mean, that's why 4-leaf clovers are so rare, by the way, because 4 is not a Fibonacci number. 3 is. Most clovers have 3 leaves. I think only something like 1 in 1,000 clovers has 4 leaves. Those are very rare. That's why they're considered lucky. Um, and another really interesting thing is that this is a sunflower. And you'll notice that there are these kind of spiral patterns going around. And if you counted the number of spirals going, you can do this in 2 different ways. I think they show blue spirals here, but there's also red. So there's blue spirals going counterclockwise, but there's also red spirals going clockwise. I don't know if you can see those. But if you counted the number of spirals going clockwise or counterclockwise, you get Fibonacci numbers. As a matter of fact, you get 2 different Fibonacci numbers. I think for this example, you get I think you get 13 going counterclockwise and 21 going clockwise. You can check for yourself. But I think this is really interesting. And it's not just a coincidence this happens. It turns out it's the most economical arrangement of flower petals. It's the way flower petals get the most sunlight without blocking the other petals. You can work out the details, and it turns out that the most economical arrangement involves Fibonacci numbers going in each direction. Pretty neat. And so that's kind of Fibonacci numbers in nature. And there's a lot of really amazing properties of Fibonacci numbers. I'm just kind of scratching the surface in this video. There's a whole journal called the Fibonacci Quarterly. And as a matter of fact, there's the Fibonacci Society, which writes it. It's been out since 1963, and I've actually published 3 papers in this journal myself. Some pretty advanced papers involving Fibonacci numbers. It's a journal devoted to properties of Fibonacci numbers and related sequences. There are a bunch of related sequences, closely related. There's another sequence called the Lucas sequence that's very closely related to Fibonacci sequence. It just starts with different initial conditions. Instead of starting with 0 and 1, you start with 2 and 1. You get these weird identities involving Fibonacci numbers. It turns out they're formulas for the sums of arbitrary powers of Fibonacci numbers. For instance, if we call Sn, so here they're saying Snp is the sum of all the pth powers of the first n Fibonacci numbers. And it turns out there's a formula for these. And the slide only shows you Sn1 and Sn2. It turns out the sum of all the Fibonacci numbers up to Fn is equal to Fn plus 2 minus 1. So, for instance, the sum of I think I mentioned let's see, the 5th Fibonacci number is 5, the 7th is 13. So if you did 1 plus 1 plus 2 plus 3 plus 5, that's equal to 12, which is 13 minus 1. 13 is the 7th Fibonacci number. So you just kind of skip ahead 2 and subtract 1, and that gives you the sum of the first n Fibonacci numbers. You can try it with different examples if you want. And there's also a formula for the sum of the squares of the first n Fibonacci numbers, and this turns out to be the product of the n plus first and the nth Fibonacci number. Pretty neat. Who would have thought? Yeah, and there's also, like I said, formulas for higher powers as well. I think I already showed this picture. I think I'm going backwards. And then there's a really useful formula for Fibonacci. You might wonder, you might think that the only way you can calculate Fibonacci numbers is to calculate all the previous numbers in the sequence. Actually, that's not true. What if you wanted to calculate the 100th Fibonacci number? Would you have to add, do 100 steps like I showed you? Well, it turns out you don't. There's a formula. There's a formula for the nth Fibonacci number, involving this funny symbol phi. That's a Greek letter phi. This is what's called the golden ratio, and it's equal to 1 plus the square root of 5 all over 2, or approximately 1.618. I think here they give you to 10 decimal places. It's a quadratic irrational number, but it turns out that the nth Fibonacci number is a formula for it involving the golden ratio. It's phi to the n minus the minus phi to the power minus n all over the square root of 5. Or if you want to write it in terms of radicals, it's 1 over square root of 5 times 1 plus square root of 5 over 2 raised to the nth power. 1 plus 5 over 2 is just the golden ratio. And then you have to subtract 1 minus 5 over 2 to the nth power. And if you did this, you can do this pretty quickly on a computer, or even on a calculator, I think. You can calculate arbitrary Fibonacci numbers. Pretty neat. And it's always an integer, even though the quantities inside this complicated formula are not integers, the result's always an integer. It's always a Fibonacci number. So I think that's pretty neat. And here this is so one sort of practical application, I guess, is imagine you had trains. You had trains where the box cars have two different lengths, short or long. And it turns out that the long box cars have twice the length of the short ones. And then you might wonder how many trains you can make of a given length. And in this case, we're looking at trains of length 6. In other words, the length of 6 short box cars. And remember, the long box cars, these are the ones shown in blue. So the short ones are shown in gray here. The long ones are shown in blue. You might wonder how many possible trains are there whose length is equal to the length of 6 short box cars. Well, it turns out that's a Fibonacci number. It turns out it's F7, in this case 13. So the number of trains of length n short box cars is Fn plus 1. So for instance, there's only one Fibonacci train of length 1, but there's 2 of length 2, that's F3, because you can either have 2 short box cars or 1 long one. And then for length 3, there's 3 possibilities. You can have either 3 short ones, 1 short, 1 long, but then there's 2 ways you can do that. Long, short, short, long. And you can keep going like this. And turns out it's always a Fibonacci number. Pretty neat, I think. And this is something called the Zeckendorf representation. It turns out that there's actually a representation of numbers involving Fibonacci numbers. This is called the Zeckendorf representation. And I have to explain what this slide means. It turns out that every positive integer has a unique expression as a sum of non-consecutive Fibonacci numbers. For instance, 1, that's the first positive integer, that's just equal to F1, which is 1. 2 is another Fibonacci number, that's F3, it turns out. I think it's better to say F2 is 1. So 2 is equal to F3, 3 is equal to F4, 4 is equal to F4 plus F2, F4 is 3, F2 is 1, 5 is equal to F5, 6 is F5 plus F2, 5 plus 1, 7 is 5 plus 2. I'll just say what the Fibonacci's numbers are. I won't say the index. But 8 is, that's a Fibonacci 2. That's F6. And then 9, F6 plus F2. 10, F6 plus F3. You can keep going like this. And notice that no 2 are consecutive. You never have 2 consecutive 1s in the Zeckendorf representation. It looks a little like binary, but it's not binary. These places represent Fibonacci numbers, not powers of 2. So I think this is kind of neat. So and here's a nice sort of graphical representation of the Zeckendorf representation. This is like the Zeckendorf representations of all numbers up to, I think, 100. And you notice these big blocks on the left. These you get the beginning of these big blocks always at a Fibonacci number. So I think the last one in this picture might be 55. I'm not sure, but Yeah, so I think this goes up like 89, but this big blue block on the bottom, I believe, is 55. So when you get to number 55, that's a Fibonacci number, but then you add, when you go beyond 55 all the way to 89, you're going to get, smaller Fibonacci numbers added onto it. And it turns out the last one before the next Fibonacci number is always every other Fibonacci number. So for instance, and then actually this is another identity I didn't mention. If you took the sum of every other Fibonacci number, you always get the next Fibonacci number minus 1. So for instance, if you did like F55 plus 21 plus 8 plus 3 plus 1, those are all the every other Fibonacci number going down, starting with 55, that's going to give you 88. You can check that yourself. That's true for every set of alternating Fibonacci numbers. And the next one's going to be F11 at 89. So it has this kind of nice pattern to it. Anyway. And this is I think this is the last slide. This is going to be a short video. I'm usually going to do this for an hour. I guess I didn't prepare an hour lesson today, but you might recognize this triangle in this picture. This is Pascal's triangle. These numbers in Pascal's triangle are what are called binomial coefficients. You probably saw this. I mean, this is very basic. You see this in probability theory and in statistics. In case you're not familiar with Penrose's triangle, I'll just go over it very briefly. It's a triangle where the numbers on each edge are all 1, and then the numbers in the middle are just the sum of the two numbers above it. So, for instance, if you look at the third row, you get 1, 2, 1, and 2 is because the two numbers above it are 1 and 1. And then for the fourth row, you get 1, 3, 3, 1, 3, because 3 is 1 plus 2, or 2 plus 1. Keep going like that. This gives you Pascal's triangle. And what's neat about, you might wonder if there's a relationship between Pascal's triangle and Fibonacci numbers. It turns out there is. And this is a pretty remarkable relationship. If you notice these kind of weird diagonal lines, these kind of diagonal lines going up and to the right, if you add up all the numbers along each of those diagonal lines, it's always a Fibonacci number. So for instance, the first line just hits the top one, so that's 1. That's F1 if you like. And then the next one hits the 1 in the second row on the left. That's also 1. But the third one hits 2 1s. It fits the first row of the third column, and then it hits another one on the right side of the second column, and that's 2. And then you can keep going like that. The next one's 1 plus 2. The next one's 1 plus 3 plus 1. So, and these are all Fibonacci numbers. So I think that's pretty amazing that you get the Fibonacci sequence inside a Pascal's triangle. Anyway, I think that's the last thing I prepared in this lesson for today. So, like I said, this was a short lesson. But anyway, I hope I've aroused some of your interest in Fibonacci numbers. You can always leave comments or ask questions. And please leave some feedback, because I need feedback from you guys about what you'd like me to do in future videos. There seems to be a lot of interest in number theory. Fibonacci numbers are kind of basic number theory. And like I said, I just kind of scratched the surface with Fibonacci numbers. There's a lot more I could say about them. So I'll probably do a few more live streams on Fibonacci numbers. But anyway, that was today's live stream on Fibonacci numbers. I hope you enjoyed it. Thank you for watching. Long live math, and I'll see you guys next time. Bye.